We finished off the last one talking just about the electronegativity, right? Where electronegativity is how strongly one atom pulls an electron from another atom, okay? Remember, the ion is, what happened in an ion is the lithium lost its electron to the fluorine, didn't it? So the fluorine took the electron away and it had full control and ownership of that electron as if it was its own. Now, then we looked at nitrogen, we looked at oxygen, we looked at fluorine, we looked at hydrogen. They had single electron bonds, covalent. They had perfect sharing of electron time, right? Now, what happens in systems where we don't have an ionic or we don't have pure, perfect sharing? There's sometimes when somebody gets more electron time than somebody else, right? Now, what do we do in this situation? Well, in this situation, we have to come up with a way of identifying what type it is, because it's going to have an effect on it. And what is the effect going to be? Okay. The effect is going to be an unequal sharing of electrons, isn't it? Let's just look at it in terms of let's say, over here, ionic is up there, and pure covalent is down here. Well, what is the limit? Well, it's the delta electronegativity. Okay? If our electronegativity difference between the two is bigger than 2.1, okay? Some textbooks, some things say 1.9, but let's just forget that and take the concept, right? The concept is that above a certain point, whether it be 2.1, 2, 1.9, whatever you have, above there, it means the electron is taken away, it loses control of its electron, therefore it becomes an ion with a full charge, a +1, a +2, a +3 even, okay? Now down over here is where we had pure covalent, totally unselfish. Let's get together and share everything, okay, amongst each other as best we can, right? That's what we're saying down there. But now, what happens in between? What happens if we have something that actually has a, let's take, for example, hydrogen chloride, okay, hydrochloric acid. Well, we've got H and we've got Cl. Remember, let's have a look. We had 1, 2, I know we had one space over here, and hydrogen, remember, had only got 1, okay, and it's quite apt I do that. That goes, now we have HCl, don't we? They are bonded. Well, let's have a look how they're bonded. What actually happens? Let us take the electronegativity of chlorine. The electronegativity of chlorine is going to be 3. So we say electronegativity is 3 of the chlorine, right? Let's take the hydrogen is 2.1, right? Now we take 3 minus 2.1, just complete it there. Delta electronegativity is equal to 3 minus 2.1, which is going to be equal to 0.9. Okay? Now what does that mean? It means that it's not ionic, but it is not pure covalent either. It is over here. It's got an electronegativity difference of 0.9. All right? Well, what happens if we had electronegativity differences of, let's say, 1.9? Right? Essentially, the way to visualize it, I think a way of doing it, is to say to yourself, right, an ion is A and B. 2 different products, sodium chloride, lithium fluoride, what we had. An ion is that the electron is there. It is never there, which means that this is plus and this is -1. Right? That's an ion, isn't it? Now, what happens when the electron is shared a bit with the other side? Right? What is happening is my electron is going around here, goes around there, goes around there, and then every now and again I allow the electron to go there, right? I'm not that totally selfish. We allow the electron to go there. Can you see what is happening here? Okay. Every third one I'm going around the other side. 2, 3, and one more around the other side. You can see from that diagram, right, that around the one side it's very dark, right? Around atom B it's dark. Around atom A it's not dark, it's light grey, all right? So what are we saying? We're saying that part of the time the electron is around A. A little bit of the time it's there, okay? Not a lot, but it is there. What does it mean? It means then that the charge on the A side isn't always +1, is it? Every now and again the electron swings by and takes a bit of the positive away, right? The other side isn't totally always negative. Let's assign a percentage, right? I said that basically 3 times once, right? So this would be then 3/4 of the time the electron is here, okay, and 1/4 it's here, okay, all right. So 3/4 it's on that side, 1/4 of the time it's on that side. So, and I mean this is just to illustrate the point. This is not an actual number that we use. Just trying to get the concept across. What does it mean? It means then this side, okay, isn't 1 plus minus 1, it's minus 0.75, right? 75% of the time it's negative, right? What here? Here it says that this is plus 0.75, okay? In other words, 75% of the time it's positive. 25% of the time, 1/4 of the time, okay, it's neutral because my electron comes swinging by, right? And ditto the other side. Please, they're not numbers, it's just a concept to do it. We could have a situation where we've got A and B, and over here we've got minus 0.5, plus 0.5. 50% of the time, the electron is here. 50%, the electron is there, all right? So there's an unequal sharing of electron time, okay? Critical concept. The electron time means that most of the time it's here, but then it shoots there, then it's here, then it's there. What type of molecule is this AB? What does it look like? Well, they're joined together, right? So we've got an A and we've got a B. They are joined together like that, right? But this molecule, partly, that means small amount. This is the small delta. Small amount, it's negative. This side is positive. This is called a dipole. Why? It's got a negative and a positive side to it, right? Remember, an ion is like the ultimate dipole, isn't it? It's got purely negative, so we call that an ion. But here, it's partially negative, only part of the time. So that molecule is a dipole, but we are still sharing. So it's a dipole, but it is covalent. And we call it polar. Polar, covalent, it's got a north and a south pole. It's got a minus and a plus pole, right? It's got two poles like a magnet, but these are electrostatic. Positive and a negative side. Okay? Now, this concept is kind of like important because it's going to tell us how things bond when this molecule, okay, comes along. All right. Now remember, he now looks like this, right? He looks like my little magnetic bullet here. The one side is positive, the other side is negative, right? Now, if we are up here, all right, let me just scroll back up. If we are in this area over here, my A and my B over there, right? This side is my, let's call this the negative. the positive. Let's say that this is like a 0.9 negative. It's almost an ion. So it's actually very strong. Down here, we could have one as a 0.1 negative and a 0.1 positive, right? Because it's almost equally shared. So can you see that this one here is strong dipole? This here is a weak dipole. Why? If it's almost ionic, delta electronegativity to almost 2.1, the electron is virtually never here. Okay? This is positive. It's sitting at the other end, which is negative. All right? So as a molecule, it's got an end which is very negative and an end which is very positive. Right? Down lower, basically, it's got an end which is sometimes positive, sometimes negative. So it's weak. It's kind of got no direction. It doesn't really care, if you like, right? It's so close to perfect sharing. So between these 2 points over there, right, and the cutoff usually is at 0.9 here, we say that above, let me redraw that neatly, okay, we say that delta electronegativity above 2.1, it's ionic, and obviously the next form up is the metallics, right? Down here, okay, they normally say delta electronegativity 0.9. Below there, it's too weakly covalent to be of interest, so we say that this is going to be covalent. Over here, it's weakly polar covalent, and up top here, just below somewhere there, change electronegativity is going to be strongly polar covalent, right? This is important, very important, because when we get to a situation where we now start talking about the actual molecules themselves, because now we've got this one, right? Now we've got one, right? We have got one of these. But they are going to go and form up with others, aren't they? Right? They're going to join to form other molecules, because when we've got water, we don't have them one at a time. We've got a whole load of molecules together, right? Let us have a look at let us take, for example, water, shall we? Okay. Let me just get to my table. Okay. We've got here hydrogen electronegativity of 2.1. So we'll take our oxygen. Okay, we'll take our oxygen, and recapping, we know oxygen had, okay, 2, 3, 4, 5, 6, okay, 2 spaces, and we know that hydrogen comes in there, and hydrogen comes in there. Yep, it's got 2, everyone's accounted for, H2O. Now let's just split this into a little stick diagram, shall we? So we'll have an oxygen over here, and we'll have a hydrogen this side, and a hydrogen that side, okay? I purposely made it bent like that, because we're going to go back and do, when we've got through this, we're going to go back and do this whole concept of the shapes, how to predict the shape of the molecule, trigonal, planars, and all of those things. But I want to rather do the basics first, okay? Let us take, now, I'll tell you what, let's take oxygen as green, right, shall we? Right, so what have we got? We've got an oxygen sitting over there. Hope you guys can see this, right? We've got oxygen sitting over there. There it is. It's green. It's environmentally friendly. It's what we need. And along come our 2 hydrogens, and they link up. We know they link up because we know that we get that sharing there of the thingies. Okay? Now let's have a look at the electronegativities, but we only look at it on a side, okay? So we take that loop there first, all right? and look at the electronegativity differences of this. We say that oxygen is an electronegativity of 3.5, I think it is. Yes. 3.5. And we say hydrogen's electronegativity. Okay. Let me just make that a double dot. Hydrogen's electronegativity is going to be 2.1. So let's take the 2 away. So our delta electronegativity, change in electronegativity, is going to be 1.4. So on our little table, let's just recap that table. Let's just go up to the table so I don't draw it. We said we're at 1.4, so we are kind of over here, aren't we? H2O has got a delta electronegativity 1.4, so it's tending towards being polar, isn't it? What is happening is that the hydrogen, the oxygen, is taking the electron this side, right? So this here is taking the electron away from the hydrogen and keeping it onto the oxygen side, right? So there's more electron time spent in around the oxygen, okay? So this side becomes negative, this side becomes positive. That wasn't a very nice delta, was it? Okay, like that. Okay, so what are we saying? We're saying because it's quite strongly polar, the electron is moved up to the oxygen side and it leaves the hydrogen with less electron time. So more electron here, negative, less electron, positive side, right? And ditto with the electron on that side. We can say to ourselves, right, we're delta minus here, we're delta plus there. Which means that now we've got this, right, this over here, our molecule of water is polar covalent. Covalent sharing. Covalent's only telling us whether it's ionic or covalent, which is the share, but it's the most important thing, it's polar. Which means what? Well, it means if we put more of these oxygen and hydrogen molecules together, called water, what is going to happen is this, isn't it? Okay? Let's draw another one of them. Well, what's going to happen is it's going to look for what's going to be attracted here. Correct? The oxygen side, which was negative, right? Now don't forget that's got 2 hydrogens over there, right? Okay, and they are positive sides there, right? What happens is that we've got another one coming along, right? Let's just get one out here. We've got another one coming along, right? And what have we got? We said, right, this, remember, the oxygen was negative. This is negative. So this one's going to fly by and be repelled, isn't it? But what's going to happen when a hydrogen side comes along? It's going to tend to bond with the oxygen. We're going to get a bond forming between these two, aren't we? We're going to get this. They are going to stick together like that, right? And then they're going to move, and they're going to find more and stick together more and more and more until we've got a whole load of them stuck together, all right? And they start to eventually look like what? Well, I guess like that, right? There we go. They've stuck. They've stuck. They've stuck. So we start building up millions and millions and millions and millions and millions of them, right? Until we've got a glass of water, I guess. They all build up together. That's what we're looking at in this process, is defining how to put the forces together, because we're moving towards not only the forces between the individual atoms, which is the electrostatic force, right? We're now saying, right, you're bonded, you're sharing your electrons, you're covalent, but more electron time on one side than the other means you are polar. If you're strongly polar, okay, you're going to be highly attractive to other charged particles, right? whether it be negative sides of a dipole, which is our polar, remember, one side negative, one side positive, or to an ion or something else that is charged. To an uncharged particle, well, okay, you're not highly attractive, but you can do certain things to that charged particle. That's where we're going to be starting to induce dipoles, okay? So basically we've got through quite a chunk of that, okay? Because I want to get on to bonding energies as well, because obviously when we put these electrons together, right, and we've got these things all formed, right? We've got our thing formed like that, right? There we are. We're all stuck together, right? Our electrons are shared. They're in their parking areas. We're all nicely, okay, BFFs or whatever we want to call ourselves. What do? Now all of a sudden that we can actually break this apart again, because that's what we need to do when we start to look at certain chemical reactions. We have to break those bonds apart. So the bond, each one of those bonds, you think of it as an electron stuck to another one, we can pull them apart. That's the whole bond energy concept, right? I'm going to look at bond energy, bond lengths, okay? We're going to talk about that. Then we're going to go on to intermolecular forces, which is the forces between the different kinds of molecules that we formed.